So welcome to a new session of macromechanics. This session will deals with 3D stiffness and compliance matrix. Now you see this laminate. So there is different fibers are there reinforced into this matrix. So this is called one laminate structure. We'll see. So for a general anisotropic material, you see this each system there will be sigma 1 in this particular surface. So there will be sigma 1 sigma 1 sigma 1 So for each session, for each surface there will be stress system. So in total we can say this is there is the stress sigma 1 sigma 2 sigma 3 like this tau 2 1. So there will be 9 into 9 elastic constant. So for one general anisotropic material there will be 81 elastic constant right from C triple 1111 to C 2121. Now similarly, if this is called stiffness matrix, this is called stiffness matrix. Now if this opposite the strain, similarly the strain matrix epsilon 1 epsilon 2 will be equal to S matrix into sigma matrix. This S matrix is compliance matrix. Compliance matrix. So as you see, this sigma ij is nothing but your Cij into epsilon kl, or epsilon ij equal to Sij kl into sigma kl. This C matrix is stiffness components and S matrix is compliance component. So we can clearly see the compliance matrix is the inverse of the stiffness matrix. So in general it would require 81 elastic constant, as I told, to characterize a material properly for one generally anisotropic material. Now however, due to symmetry of this stress and strain tensor, the sigma ij equal to sigma ji or epsilon ij equal to epsilon ji, so it will be reduced to your 36 elastic number of elastic constant for anisotropic material with symmetry. Now generally this is the stress strain relation for one anisotropic material. So sigma 1 sigma 2 sigma 3 tau 4 tau 5 tau 6, which can be represented as this stiffness matrix, that is 36 6 by 6 matrix into epsilon 1 epsilon 2 epsilon 3, this gamma 4 gamma 5 gamma 6. Now there is, this is micromechanical analysis. So stress strain relation, so sigma I is equal to Cij epsilon j, this is C is nothing but stiffness matrix, epsilon I equal to Sij sigma j, S equal to compliance matrix. So there are 36 constant related to the stress strain components, which will be further reduced to 21 constant due to symmetry of the stiffness matrix. So we will see this one. So we will consider this energy consideration. Thus work done per unit volume equal to W, which can be half Cij epsilon I epsilon j. Now this stress strain relation so can be obtained one differentiating. So sigma I will be Cij into epsilon j. Similarly sigma ij again differentiate del square W by second derivative of W by del epsilon I del epsilon j. In similar manner we can Cji also we can calculate, you can got this one. So as we will compare this one, so Cij is nothing but your Cji, or this compliance matrix compliance component Sij will be nothing but your Sji matrix. Now this it is clear that subjecting to anisotropic material to inaxial stress makes the body under both axial and shear strain. These are coupling. Thus the stress strain at a point can be described by 6 components. However, Hooke's law, this anisotropic material, there are 21 independent constant. 21 independent constant. So there are not any planes of symmetry for the material property in this kind of material. So what is specially, or what is the stiffness condition, stiffness system of specially orthotropic material. As you will see, the reference system of coordinates is selected along the principal plane of the material symmetry. So here you will see there is no interaction exists between normal stress sigma 1, sigma 2, sigma 3 and shear strain, or shear stress with normal strain, and no interaction exists between shear stress and shear strain. So we will calculate, we will see the stiffness matrix as will looks like this way. Now transversely isotropic material. Orthotropic material will be called as transversely isotropic when one of its principal plane is a plane of isotropy. That is, at every point there is a plane on which mechanical property are same in all direction. So this is this is the condition of transversely isotropic material. Next we will see orthotropic material under plane stress. Now what you will see, isotropic material. Now this is the condition of isotropic material. One isotropic material is characterized by an infinite number of planes of material symmetry through a point. For such material, the subscript 1, 2, 3 in the material constant are interchangeable. So we can see there are only two elastic constants, C11 and C12. So finally we will see on one isotropic material there are 21 independent elastic constant. Monoclinic there is 13, orthotropic 9 independent elastic constant, transversely isotropic 5, isotropic 2. Now we will see, let's see this, consider this orthotropic material which is subjected to sigma 1 and uniaxial tensile load in longitudinal direction sigma 1. So we will calculate this epsilon 1, we will be calculating S11 sigma 1, epsilon 2 S12 sigma 1. Similarly you can calculate each of these terms. So now let's take this one, sigma 2 is acting in transverse direction. We can calculate this epsilon 1, epsilon 3, S12. So similarly we can calculate if your pure shear force is acting, we can calculate tau c. This components matrix constant, each of these constant we can calculate S12, S23, S23, S33. So all this will given one condition we will calculate these terms. Now finally we can calculate this test and relationship can be expressed in terms of engineering constant. So epsilon 1, epsilon 2 will be equal to this components matrix. So 1 by E1, this is nu 2 1 by E2, nu 3 1 by E3. So these are stiffness components matrix. Now for the symmetry of the components matrix, nu 1 2 E by E1 equal nu 2 1 by E2, or nu 1 3 by E1 equal to nu 3 by E3, or nu 2 3 by E2 equal to nu 3 2 by E3. Similarly, this stiffness matrix can be expressed by inverting the components matrix. So we can calculate this C11, each of these terms of stiffness matrix. So if we will see this stiffness matrix, we will see all these terms C11, C22, C33, C12, C23, C13, 4 4, 5 5, 6 6. All these terms of stiffness matrix can be calculated using this procedure. Now you see orthotropic material under plane stress. Plane stress, so there is no Z component. So in most structural applications, this composite material are used in forms of thin laminates loaded in planes of laminate. Thus, this composite lamina or laminates can be considered to be under a condition of plane stress with all stress condition in the out of plane direction. So this is one reduced stiffness matrix. Using this plane condition where there is no terms of this Z value, Z coordinates, so this reduced stiffness matrix sigma 1, sigma 2, tau 6 will be Q11, Q1 to 0, Q1 to Q2 to 0, 0, 0, Q6. This is called reduced stiffness matrix. Or in opposite, the strain will be S matrix into stress matrix. This is called reduced compliance matrix. So here we can, using this We can calculate this S11, S12, 22, S6 terms. All these terms we can calculate using this general mathematical formula of a matrix. So similarly Q1, Q2, Q1 to Q6 also can be calculated, which will be in terms of E1 and nu12, elastic modulus and Poisson ratio. So that's for this session. Thank you. We'll see a new topic in our coming session. Thank you.